Wanted to work through a problem that involves momentum. It involves classical momentum and relativistic momentum, and a comparison of classical momentum and relativistic momentum. So the question asks, at what speed or how fast does a particle travel such that the relativistic momentum of the particle and the classical momentum of the particle differ by 10%. So to go ahead and calculate this speed, let's first just imagine our particle. Here it is, traveling from the left to the right. It has some mass, it has some speed, and it has, if it was a classical particle, a classical momentum. I'll call that P subscript C for classical. It has, if it's a relativistic particle, some momentum. I'll call that P subscript R for relativistic. Now, before we do the calculation, let's just remind ourselves of the two equations for the two momenta, the classical momenta and the relativistic momentum. So classical momentum, P subscript C now, is just the product of the mass and the velocity of the particle. Relativistic momentum is the product of the mass of the particle, the speed of the particle, and also the Lorentz factor gamma. So gamma mv. In this problem, right, I'm just going to worry about the sizes of the momenta, not the directions of the momenta. So we're just going to think of these equations as equations for the sizes. The size of the classical particle's momentum is mv. The size of the relativistic particle's momentum is gamma mv. Now, in this particular problem, we're told that the relativistic momentum and classical momentum are different. If you remember that the Lorentz factor is 1 or bigger, it must be that they're different because the relativistic momentum is larger than the classical momentum. And so it must be that PR divided by PC, the ratio of the relativistic to classical momentum, is 1.1. This is 10% larger than them being equal to one another. Okay, so now let's set about calculating the speed at which the ratio of the two momenta is different by, the ratio is 1.1. The two momenta differ by 10%. So I'm just going to start by writing down PR over PC, filling in the expressions for the relativistic momentum, gamma mv, and the classical momentum. We can see that the masses cancel out. The speeds in mv cancel out, and we're actually just left with this gamma factor here, or this Lorentz factor here. So if the ratio of the momenta, classical to relativistic to classical momenta is 1.1, it actually means that gamma itself must be 1.1. And so that's going to be our real starting point. This question is really telling us that gamma, the Lorentz factor, is 1.1 for this situation where the relativistic momentum is 10% bigger than the classical momentum. And we're going to find out what speed gamma or 1.1 actually corresponds to. So to do that, we've got to remind ourselves of the equation for gamma. It depends on the speed of the particle. It involves the ratio of the speed of the particle to the speed of light. And it's given by this little expression here. So it's inside the parentheses 1 minus v over c squared. And then we take the square root of that. We take the inverse of that. So the power is -1/2. If I want to rearrange this equation for v over c, i.e. the quantity in the right-hand side in terms of the quantity on the left-hand side, what would I do? Well, what I would do is probably square up both sides so I can get rid of the 1/2 over here. So I'd get a gamma squared over here. I would take the inverse to get rid of the 1 over the power of -1 after carrying out the squaring. I then move terms from the left to right. When I do that, I would get that V over C squared is going to be 1 minus 1 over gamma squared. And if I take the square root of that, I'm going to get a 1/2 factor over here as the power on the right-hand side. And so I obtain the result that V over C is equal to the square root of this quantity in parentheses involving gamma factor. So at this point, I could stick in the numbers. So the gamma factor we learned is 1.1. And this 1.1 has to be squared. And then I've got to divide by 1, the 1.1 squared. Then I've got to take the difference from this one here. And then I've got to take the square root of that quantity. And if I do that, I went ahead and did that. I got that V over C is 0.417. That is, another way of writing it, is that V itself is 4.17 of the speed of light. It's 41.7% of the speed of light. So that's kind of the magic momentum, magic speed, at which the, if you're traveling at that speed, 41.7% of the speed of light, then your momentum is 10% greater than your classical momentum if you were traveling at low speeds.